An important physical phenomenon and a source of transport in the microfluidics and the microscale is diffusion. What's diffusion? Diffusion is by definition the net movement of a substance from a region of high concentration to a region of low concentration. And I expect that you're all very well aware what diffusion is. You have learned that in your basic physics lecture, so I'm going to go rather quickly over that. Diffusion formally can be described mathematically with two formulas. One is the diffusive flux J, which equals diffusivity constant times minus a concentration gradient. So the gradient, of course, delta C being equal to delta C delta X I in the different directions, or in a certain direction X, yeah. And this is the first. Law of Fick, and the second law of Fick tells that the change of concentration with time, and C is always a matter of space and time, but the partial derivative of the concentration must equal diffusivity times the Laplace operator of the concentration, and delta C here being equal as delta C delta X1 square plus delta C delta X2 square plus delta C delta X3, second partial derivative in the three directions. So these two formulas, these are Fick's first and second law, describe entirely how diffusive action will work on a certain concentration field. What is important is that if you combine these, you will see that in a certain for a certain concentration field, you will find that a typical diffusion length, so the typical length that a species will diffuse under a certain amount of time, equals more or less 2 times square root of d times t, diffusivity times time. And that's kind of, that tells you, yeah. So that this law here, this estimation of diffusion length, actually tells you why is diffusivity so important on the microscale. It's because on the microscale, all, I mean, on small channels, for example, the distance are very small. So you see within a very short, if the distance is small, within a very short amount of time, you will have diffusion over the entire width of a channel. So diffusion will be a major transport mechanism. And to just give you some examples of how small that is, so for example, for a, let's look at diffusivity in water. And let's see, gas, like the most common gas is nitrogen. So nitrogen in H2O. We have a diffusivity D, typically 10 to the power minus 6 square meter per second. So in 1 second, we'll have LD equals more or less 2 millimeter. Can calculate that. So in 1 second, the nitrogen molecule in water can diffuse up to 2 millimeter. Now in microfluidics, typically very often microfluidics are going to be for medical applications, for example for diagnostics, and for example a typical object that we're going to see is a protein. So let's see, for a typical protein of size typically 5 to 10 micrometer, we talk about like 100 kilodalton sized object, 5 nanometer sized particle. We'll find a diffusivity in the range 10 to the power minus 10 square meter per second typically. And we'll find that in 1 second, LD will be more or less 20 micrometer. So protein will diffuse roughly somewhere like 10-20 micrometer per second. Just to give you an idea. The next fundamental physical microfluidic principle we're going to talk about is mixing. And mixing is important, and it's difficult in the microscale. So we have now seen here that diffusion is a major transport mechanism, and typically for objects like proteins we'll have diffusion like per second, like 20 micrometer per second. So if I have a microreactor, I see like if I have a microreactor that is typically, say, larger than, say, 100, 200 micrometer large, but then, like if it's, say, below 100 micrometer, I will have a lot of diffusion. Within 10 seconds somewhere, diffusion will make sure that I have enough mixing in that very small scale. However, if I go above, say, typically like a 50, 100 micrometer sized channel or a reaction chamber, then diffusion will not be enough, and I will need mixing to have a good mixing of active mixing to get a good mixture between different molecules. But we have seen that microflow is laminar, so the molecules tend to stay in their streamline. Yeah, there's no turbulence acting. The Reynolds number is very low. So typically sizes, say, channels below 2-3 millimeter down to 100 micrometer, that scale typically will be very difficult to get mixing. Yeah, it is too large for diffusion and it's too small for turbulence. So this is the microscale region where we often we see mixing is going to be difficult because we have a laminar flow and diffusion is not enough, so we'll need to add convective flow in our system. But it's laminar, so we'll have a lot of frictional force, so we're going to need a lot of energy and specific strategies to mix liquid on that scale. Before I go into micro mixing, I will talk a little bit more about chaos theory. And why I do that is that because the micro mixing phenomena we're going to use are often going to be based on chaotic, like linked on chaotic systems. Now, chaos theory. I really hope that you have in your previous curriculum learned about chaos theory. It is one of the most important theories of the 20th century. So we have quantum mechanics, we have relativity theory, and I would say chaos theory is one of this, one of this super important theories that have been worked out. And what is chaos theory actually? What is chaos theory and why is it important? Let me introduce that. So what is chaos theory? Chaos theory actually is a mathematical theory. It's not a physics theory, it's a mathematical theory. And chaos theory studies the behavior of dynamical systems. And dynamical systems that are very sensitive to their initial conditions. So a dynamical system is a system with dynamical variables. So I have typically, typical example is a hunter and a prey system. So I have one variable telling how much prey I have, and one variable that tells me how many hunters I have in a certain ecosystem. And the more hunters, the hunters will eat the prey, and so the more hunters, the less prey I'll get. But the more prey, I mean, they reproduce. So the more prey, the faster they reproduce, and you'll see this: the concentration of hunters and prey in a certain ecosystem will vary over time, constantly, depending on how many of each species you have. And that is what I call a dynamical system. So in this case, I have two dynamical variables that can vary over time. And a large class of dynamical systems are chaotic, and that means that if I take, for example, hunter and prey system, if I have a starting condition of a certain amount of hunters and a certain amount of prey, very well determined, then I can follow the evolution of both the amount of hunters and prey over time. If I change that amount with a very tiny fraction, like maybe I have 20 hunters and 1,000 prey. If I go to 20 hunters and 1,001 prey, and I put my formula in, I may find that my system behaves, in the beginning it will behave similar, but after a short time it will start behaving entirely different. So although my initial condition changes very, very little, only 1 in 1,000, I will see that the result of that is going to be dramatic. It's going to be dramatically different evolution. So a chaotic system is a dynamic system that is extremely sensitive to beginning conditions. And that's a mathematical, it has nothing to do with physics, it's a mathematical concept. Yeah. So basically that means that although the system is entirely deterministic, it is not predictable, because in a reality it will be very, very difficult to know exactly what is exactly my initial condition. Yeah. So basically the limitation in precision of knowing what is my initial condition of a system will mean that it will be entirely unpredictable towards the future. See, the system is entirely deterministic, but I don't know the exact initial conditions, so I don't know what the outcome will be. And this is what chaos theory is about. And a good example is, of course, a weather system. And to teach you a little bit more about it, this is a course in microsystem. It's not about chaos theory, but I want you really to. This is such an important concept. Because all physics is actually chaotic. In reality, everything is chaotic. A physical system is only linear, and you can only describe it using your nice analytical formula. You can only do that for very short time frames and very short, well-known positions. Because over a longer time, everything will become chaotic. So, if you want to study physics, you actually have to know chaos theory. So, to give a short introduction, I want you to watch I think, an 8 or 10 minute movie that tells you a little bit about what is a chaotic system and how is that linked to fractals and to some of the strange attractors, etc.